Hi, my name's Andrew Livingston. I'm your lecturer for CTR08108, which is Civil Engineering Principles and Materials 2. This is just a catch-up video of what was discussed in class. It's more of a summary of what was in class, not everything can I capture in this video, but we're going to do the best we can. In addition to the lecture, there's on Moodle you will find additional tutorial questions with the answers as well. Okay, let's crack on to the slides. So this is the first lecture in this module, and the main title is Hooke's Law of Linear Elasticity. So a quick backstory on Hooke's Law, or the assumptions in Hooke's Law. There is a relationship between the applied force and the resulting deformation in various objects, beams, rods, and so forth. And we have that linear relationship as what the assumption is, or simplification is. Now this does hold true for most objects in most situations. However, there are some exceptions. The exceptions are when there's the force goes beyond which that law no longer holds true. So up until a certain point, that rule would stay true. Or if there's a complex internal structure within the material, then yeah, that law may not follow. So is it an assumption? It's a good assumption as well, and we use this throughout. This is just a summary of what we'll be covering within this very short lecture, ending in axial stiffness. So let's go to our first example. Say we've got a bar, and the bar has a length L. If we apply a force F at the end of the bar, it should then deform or elongate, and the new length is called Li. That deformation or elongation we'll refer to as delta. Pardon me. So we have an axial load displacement relationship. F equals K divided by L, all multiplied by delta, where delta is the elongation or the shortening if it's in compression of the bar, which is Li take away L. We've got the axial stiffness of the bar denoted by K divided by L. We're going to come back to that at the end of the lecture. And for a quick summary, if we have the bar and we apply force, and as the force ramps up, put more and more force on, we're going to get more and more deformation. And the law states that there's a linear relationship. Now, there is up until a point, so let's go into that. So the assumption would be, if I apply a force, and you see here, F0, delta 0, so that's the force that I've applied. And if I let go of that, if I take the force off, hopefully you can see my mouse. If I take the force off, it should go back to its original shape, original length. If I apply a greater force on, in theory, with a linear elastic behavior, it should go back to its original shape. And then here are some equations here. Let's look at that. K, we'll refer to that as the stiffness. Now, if you can think of your equation of a straight line, and you've got M as your gradient, then just think of your K as your gradient for just now, and that'll be quite helpful. So that stiffness is your relationship to that gradient of that line. And we can say K delta 0 is going to be greater than K delta 1. So K delta 1 is smaller than K delta 0, then the axial stiffness of the bar decreases as the displacement increases. Okay, So essentially, the lower the stiffness, it means you've got more deformation. So let's talk about viscoelastic behaviour. Viscoelastic behaviour is when you apply a load on. If you take the load off, it goes back to the original shape. But if you apply a load on and you leave it on for a long period of time, you will get something, well, it's called viscoelastic behaviour. Or if you think about a beam, perhaps a timber joist, simply supported timber joist, and you apply a load in the middle and you leave it on there for 50 years, if you were to take the load off, you would expect to see a creep or deformation to have happened over that period of time, and that's that viscoelastic behaviour. That could be over a short period of time, or it could be over seconds, hours, years. Okay. Now, yep, it's following the same principle as before. So the stiffness of a load being applied for a longer period of time will have changed as opposed to the load being applied instantly and removed instantly. So that stiffness ratio, so the gradient of the line is going to be lower than if it were load on, load off. I hope that makes sense. Now, let's have a look at this linear, elastic, and non-linear and plastic behaviour. Now, when you saw the original shape of the curve, if we go back to that, there's the original shape of the curve. That doesn't look like a linear elastic behaviour, especially over here. So let's go back to where we were. So here we are. Now, with that original curve, load on, load off, it would go back to its original behaviour. The elastic displacement, now we're still talking about the viscoelastic behaviour, i.e. over a period of time. So we apply the load on instantly and we take the load off pretty soon afterwards. It'll go back to the original shape. But if we apply the load on, leave it for a period of time, say 50 years, we then take the load off, it will not go back to its original shape, it will not go back to there, but in fact you'll see some new permanent displacement taking place. Then you take the load off, put the load back on again instantly, and you'll have that elastic displacement there. An example of that would be a timber bridge. Here's such an example here. This is actually a well-known bridge. It's actually made out of Akoya, which is not for today's lecture. This is one of my projects actually. This is the Dyson Institute Village. You may remember that from your first year module. And within that, we had to calculate a number of things. We had to calculate the slip in the connection. Not just the instantaneous slip, but also the deformation over a period of time. We had to calculate that and predict that. And it's the same behaviour. We have the load on, load off scenario where there's no time involved, or you've got the time. Now that's been on site for about 8 years, I think 8 years now. So we have calculated what that would expect to be, and it's all within tolerances, but we do have that. Now, in the past, people would talk about, let me rephrase that, that's not true. People still talk about asphalt as having that viscoelastic behaviour, because asphalt absolutely does. In fact, there's a very famous experiment, here it's here, where they have got bitumen, or asphalt essentially, but bitumen within a jar, and it drips. Now, I think from memory, something like 10 years it took for the first drip, 10 years for the first droplet to fall into the glass. And I think this experiment to this day is still running. I'll have to double check that. The 8th drop fell on the 28th of November 2000. Yep, so it's running over a period. So we can see here that this asphalt, or this bitumen, sorry, has an elastic, viscoelastic behaviour, similar to which we would talk about timber having the creep effect. Similar thing. Now, let's talk about the linear elastic up to failure. In this scenario here, we've got that original curve, and we've got the F max. I'm going to call that the F max there. We are going to take the assumption that that has a stiffness, you can see here, and we're going to talk about that later on in the module. But that's going to be the linear elastic range here, in this area here. And for an assumption of things like steel and other materials and timber as well, it's absolutely, it holds true. Right, so we have the axial load displacement relationship. You've seen this equation before. We've called this equation 1 from memory. K divided by L multiplied by delta, that's the stiffness, that's the elongation. K is a constant value. But what is that value? Now, before I referred to that line as the gradient, or m in the equation of a straight line. So let's look at what k actually is as a value. So we've got two new concepts we need to introduce. We've got stress and strain. Axial stress and axial strain in this scenario, there's a round rod with a force being applied at the end, pulling it down, so elongating the rod. And the units for axial stress is newtons per millimetre square, which is force over area. So force is, for example, in newton, and the area is that cross-sectional area. So we can see the stress is the stress on that area there, anywhere in that rod. The axial strain is essentially delta, or the elongation, divided by L, and both of those are millimetres and millimetres, so that's actually a ratio. Now, it's handy to write down what the ratio is still in, even though it's a ratio and the unit is nil, but it's handy when you're doing the maths is to write down millimetres divided by millimetres in this scenario, and of course the cross-sectional area, millimetres square. Yep. So, if you look at this here, we've got the actual stress and the strain. It's the stress-strain curve, very similar to the load distribution curve from before. But we've got this equation, stress over strain equals E. E is the modulus of elasticity, and modulus of elasticity is also in newtons divided by millimetres square. So that's the unit for the modulus of elasticity. The force displacement ratio, you saw that before, equation 1, can be rewritten in terms of stress and strain as stress times A, or the area, equals K divided by L, strain L. So that's how it can be rewritten, which can be rearranged to become K equals EA, modulus of elasticity multiplied by the area. So we now have a better understanding of what K actually is. It's no longer just a gradient on a line, it's now E times A. Now E is the mechanical properties of the material being used, and A is the geometry, or the sectional area, of the rod in this example. The actual stiffness of the rod is a function of, yep, we just stated that. final remark, the linear, yeah, you can read that yourself. So let's have a look at our first example. Our first example, exercise 1. Now, we do have this exploded into more detail for further work for you to do during the week. But for just now, exercise 1, the steel rod shown in figure is subject to a tensile load of 400 kilonewtons. The rod is 800 millimeters in length and has a circular cross section with a diameter of D equals 35 millimeters. The steel used has a modulus of elasticity of 210,000 newtons per millimeter square. Now, your ask is to calculate the final elongation, or the delta, of the rod. So, looking at the equations that you already have before, why don't you stop the recording, look at your notes, and then try and work out what's happening. Okay, now that you've came back, let me try it this way. Let me try and present the solution in this manner. Delta is what we want. We've looked over our equations and we can see that strain times length gives us delta. So why don't we just write that down? Delta is what we want, and there's a relationship. We have L, but we don't have strain. So if we write down strain, now we know the equation E is the stress-strain relationship. So we can rearrange that and have strain equals stress over modulus of elasticity. We have the modulus of elasticity, but we don't have the stress. But we do know the equation for that. The equation F equals stress over area. Sorry, stress multiplied by area. We have the force, that's 400. We should be able to calculate the area, because the area is just pi r squared. So there's the area there, pi r squared. We can then get the stress from that, add it in, and we'll just work our way back up. Now that we have the stress, we can now get the strain. And now that we have the strain, we should now get the delta caused, or the elongation caused by the force F being applied. Okay, so the elongation caused by that force of 400 kilonewtons applied to that rod is 1.548 millimeters. Now, there's a number of things that you need to take great care on. The first being, let's try to see the length of the time, 18 minutes. First thing is, make sure that your units are correct. We see here, we've got kilonewtons, and that's being converted into newtons. We see here the 800 or 0.8 meters has been converted into millimeters. Newtons per millimeter square, those units are fine. We're using those as they are. The diameter, 35 millimeters. We convert that to a radius. Yep, so your units are very important. If you write down the correct numbers but in the wrong unit, then your equation will give you crazy answers. So always double check your answer, look at it and think, does that make sense? Is that a realistic answer? Now we do have a second, do apologise. So that's one way of solving that. Is there another way of doing it? Well, in actual fact, there is. There's another equation, which is F equals E times A divided by L, all multiplied by the elongation, or delta. This here, we've seen this equation before. If we just use that, and we bring delta out, we have the force, we have the length, we have the elasticity, and all we really need to calculate would be that cross-sectional area. That makes the equation much quicker and much easier to calculate without having to go through these two additional steps. And we get the same answer, obviously. Now, we do have a second tutorial here. Why don't you work this one out and make sure you've got the correct answer. Now, we do have, let me double check that I've got it loaded up. Let's see if I have. We do indeed. On the middle page, if I just switch rows just for a second. Okay, that's not helping me. Do apologise. No, I'll do it again. As I'm trying to say, on the middle page, we do have the solutions for you. Revision material, additional tutorial questions with answers. So you could go into this, load that up, and each week, so there's example number 1 that we just did, then example number 2 that you were about to look at, and then there's a further question down here, which you'll have a look at in your own time and then provide your answers for the following week. If I just go back here. Right, so this is only a very quick snapshot of what was discussed in class. Hopefully that helps those that want to recap, or for those that couldn't make the lecture. Each week I will pre-record the lecture. I'll make it available after the lecture is finished, and there will be tutorials each week that you can work through in your own time or use for revision for the class test or the exam. Okay, I hope that's all, and I'll catch you next time. Bye.